Giant, mature galaxies just 300 million years after the Big Bang. The first deep observations from the James Webb Space Telescope have revealed massive galaxies at a time when the universe was still in its infancy. Just 300 to 400 million years after the Big Bang, these galaxies already possessed stellar masses comparable to the largest structures seen today. This discovery stands in stark contrast to cosmological models that predicted smaller, more chaotic clusters during that period. What's striking is not just the number of stars, but the level of structural organization in these galaxies. Some exhibit dense central cores and symmetrical brightness profiles, indicating they had already undergone significant evolutionary phases. These observations suggest that star formation and mass consolidation occurred far more efficiently than previously expected. Webb spectroscopic data revealed heavy elements such as oxygen and carbon within these systems. The presence of such atoms implies that multiple generations of stars had already formed and died, something that requires time. This challenges the established cosmological timelines, which did not anticipate such advanced chemical cycles so early. Current galaxy formation simulations are now being reassessed in light of this new evidence. Models explaining gravitational gas collapse, large-scale star formation, and thermal energy dissipation must be updated to account for complex structures emerging within just 500 million years of the universe's origin. Another key aspect is the density of these galaxies. Many are extremely compact, with intense luminosity concentrated in small regions. This suggests that early cosmic conditions favored star formation in dense environments, potentially at efficiency rates far beyond those seen in more recent galaxies. The role of dark matter in this scenario is also under renewed scrutiny. If galaxies formed so rapidly, dark matter halos may have collapsed and drawn in gas more aggressively than previous models suggested. New simulation work is exploring this possibility. The data was primarily collected with the NIR-CAM instrument and confirmed through spectroscopy using tools like NIR-SPEC. This cross-validation ensures the findings are not artifacts, but independent confirmations of the same physical reality. Consistency among multiple galaxies at similar redshifts reinforces the observed trend. Some researchers have floated the idea of revisiting redshift calibration itself, though this is considered unlikely given the precision of the instruments. The debate currently centers more on how to interpret the physical implications of the data rather than questioning its accuracy. Ongoing analyses using gravitational lensing aim to expand the statistical base. Certain galaxies observed by Webb, such as CEERS 93316, show brightness distributions and structural features comparable to present-day galaxies. This degree of symmetry and density defies the expectation that the early universe was dominated only by irregular, unstable clusters. The presence of interstellar dust in these systems is also significant. For such dust to exist in large amounts, an advanced stellar life cycle must have already taken place. This adds further pressure on formation and evolution models, as dust directly affects the opacity of the medium and the cooling process is essential for new star formation. Research teams worldwide are using this data to recalibrate early universe simulations, incorporating revised gravitational collapse rates, radiative cooling mechanisms, and supernova feedback effects. Comparisons with data from ALMA and the Hubble Space Telescope are helping build a more complete picture of this cosmic era. The massive, mature galaxies detected so early by Webb were neither expected in such numbers nor with such complexity. The initial survey has already identified dozens of similar cases, and upcoming deep field studies will determine whether this pattern is an anomaly or a widespread characteristic of the young universe. Complex spiral galaxies appearing far earlier than expected. The formation of spiral galaxies has traditionally been thought to require billions of years of dynamic evolution, yet images from the James Webb Space Telescope have revealed well-defined spiral structures in galaxies with redshifts above 3, meaning these patterns were already present more than 11 billion years ago. These galaxies display symmetrical spiral arms, bright central cores, and density profiles suggesting gravitational stability. Data from NIRCom indicates that the distribution of stars and gas in these galaxies closely resembles that of modern disk galaxies. This implies that the processes responsible for spiral formation were already at work early in the universe. A standout example is galaxy GS 9209, whose structure and spectral data point to rapid maturation. Specific emission lines suggest that its peak period of star formation had already passed, even though it's considered extremely young in absolute cosmic terms. This supports the idea of short, intense bursts of star formation in the early universe. Spiral arms are typically associated with density waves caused by gravitational instabilities. For such patterns to emerge, a certain level of internal organization and interaction with dark matter is required. The presence of these features in galaxies less than 1 billion years old suggests that the necessary dynamic mechanisms began operating much earlier than previously believed. Moreover, these galaxies aren't isolated. In many cases, they're observed in gas-rich environments, interacting with smaller galaxies or filamentary structures. Such interactions may have helped trigger or accelerate the development of spiral patterns by introducing disturbances that organize matter into coherent motion. Spectral analysis reveals not just ionized hydrogen, but also elements like oxygen and nitrogen, evidence of prior generations of stars. This points to early chemical enrichment, a prerequisite for radiative processes that help stabilize galactic disks. Spiral formation models based on numerical simulations are now being revised, incorporating larger amounts of cold gas and more efficient gravitational collapses helps replicate some observed features, though significant gaps between models and Webb's imagery remain. These findings also raise questions about the angular momentum evolution of the early universe. The angular momentum required to maintain a spiral disk demands specific conditions of rotational velocity and mass redistribution. Researchers are now investigating this based on galactic rotation patterns detected in emission line spectra. Another key factor is the relationship between spiral galaxies and central black holes. Some hypotheses suggest that feedback from supermassive black holes may have helped regulate star formation, enabling spiral structures to persist even in dense, turbulent environments. High-resolution imaging is providing not just overall shapes, but also data to study gradients in color and metallicity. This enables estimates of the average age of stellar populations across different disk regions, offering deeper insight into the formation history of these systems. The consistency of findings across different observation fields suggests these early spiral galaxies are not anomalies. They appear in significant numbers, pointing to a recurring phenomenon in the universe's early stages. This recurrence is pushing current models to incorporate new initial conditions for galaxy formation. The data from Webb provides a rich foundation for refining theories about the origin of organized structures in the cosmos. The focus now is on expanding the sample size and identifying statistical patterns that reveal which variables most strongly influence the early formation of spiral disks. Why some galaxies seen by Webb shine as if they're older than the universe allows. Observations from the James Webb Space Telescope have revealed galaxies with properties that suggest an age incompatible with the time elapsed since the Big Bang. The light we receive from these objects displays spectral features typically associated with mature stellar populations, yet their distance, determined by redshift, indicates we're seeing them during a very early stage of the universe. In many cases, the chemical composition of these galaxies includes heavy elements like carbon, oxygen, and iron, elements that usually require multiple stellar generations to form. This implies that these galaxies not only emerged early, but also underwent rapid and intense periods of star formation and death. Their high metallicity challenges the established timeline of cosmic nucleosynthesis. Beyond their chemistry, some of these galaxies are also brighter than models predict for their estimated age. Their high luminosity, combined with dense stellar cores, gives them the appearance of much older galaxies. This raises the possibility that certain environments in the early universe were especially conducive to the rapid formation of large stellar populations. Gravitational lensing may explain some of these observations. In such cases, light from distant galaxies is magnified as it passes through massive foreground objects. This can make galaxies appear brighter than they truly are, although lensing doesn't account for all the cases reported. These detections were made possible by Webb's deep infrared sensitivity, which allows it to capture light from ancient stars whose emissions have been stretched by the universe's expansion. Spectral analysis suggests that peak star formation in some galaxies occurred just tens of millions of years after the observable universe began. These findings are now prompting revisions to galaxy formation models, especially regarding the efficiency of gravitational collapse and the role of massive dark matter halos. If such complex structures formed so quickly, either the physical processes were more effective than previously thought, or early cosmic environment had special conditions that favored rapid growth of large galactic systems. Some simulations are now exploring scenarios where galaxies formed rapidly in high-density regions where massive gas clouds collapsed at accelerated rates. These models also consider the influence of primordial magnetic fields and local anisotropies in matter distribution that could have spurred the early emergence of large galactic systems. Another possibility under discussion is that of extremely intense but short-lived starburst phases, followed by periods of inactivity. This would create an apparently aged stellar population in a short amount of time, altering the galaxy's spectral signature and leading to an overestimation of its age. High-resolution spectroscopy could help identify these patterns. The discrepancy between inferred stellar age and actual chronological age remains under active investigation. In some instances, data suggests that galaxies formed up to 90% of their stellar mass in under 100 million years, a pace far beyond any star formation rate seen in the local universe. The challenge now is to determine whether these galaxies are rare outliers or representative of a common class in the early universe. Ongoing and future observations, including those using alternative gravitational lensing angles and spectral filters, aim to establish the frequency and diversity of these seemingly prematurely aged galaxies. The implications extend beyond galaxy formation theory. They touch on radiation physics, cosmic dust behavior, and interstellar opacity, all of which affect how we interpret incoming light. The observed properties suggest that some of our interpretive tools may need recalibration for the extreme conditions of the primordial cosmos. This mismatch between appearance and actual age is more than an astronomical curiosity. It signals that we're still learning how to read the signatures from the universe's first billion years. Webb's growing dataset is expected to yield more such cases, offering critical opportunities to test and refine our understanding of a possible Population 3 star, the universe's first light. Population 3 stars are thought to be the very first stars in the universe, formed solely from hydrogen and helium with no heavier elements. Until recently, they had never been directly observed. Thanks to the James Webb Space Telescope's deep infrared sensitivity, astronomers have identified what may be one of these primordial stars. A promising candidate was spotted in an extremely distant galaxy with a redshift greater than 10. The galaxy's spectrum reveals an unusual ultraviolet emission consistent with radiation from extremely massive, hot, and short-lived stars. Simulations suggest these are precisely the characteristics expected from population 3 stars, which are believed to have had masses between 100 and 300 times that of the Sun. These stars would burn out quickly, within a few million years, ending in extraordinarily powerful explosions. The spectral signature observed shows an absence of heavy elements, such as oxygen, nitrogen, and iron. This elemental purity is one of the main criteria used to identify a population 3 object. Modern stars, classified as population 1 or 2, always exhibit some level of metallic contamination inherited from earlier generations. Detecting this chemical purity is therefore critical. Webb's high-precision spectroscopy, particularly through its NIRSPEC instrument, allows researchers to break light down into thousands of individual wavelengths to analyze its chemical composition. The pattern observed in this galaxy is currently the closest match yet found to what scientists expect from a truly primordial star. Beyond its composition, the intensity of radiation observed is also unusual. Theoretically, population 3 stars emit vast amounts of ionizing photons, capable of transforming the surrounding interstellar medium. The data suggest strongly ionized regions around the object, another marker consistent with these early energetic stars. This implies highly concentrated energy output on small spatial scales. Researchers also examined the structure of the host galaxy, which appears compact, low in mass, and with a sparse stellar population. This type of environment is ideal for uncontaminated star formation, as it likely hasn't undergone previous star-forming cycles. Its location and context further support the hypothesis of an extremely ancient origin. The detection remains preliminary. Scientists emphasize the need for more observations to confirm that the emission isn't coming from another rare source, such as a growing black hole or a galaxy with extreme properties. The data are precise, but interpreting them relies heavily on complex theoretical models. If confirmed, this would be the first direct observational evidence of a population 3 star. Such a discovery would open new doors to studying the earliest starlight, the first supernovae, and the origins of heavy elements. Until now, our understanding of these phenomena has come solely from simulations, without direct empirical evidence. Webb may have changed that. The search for these stars continues on multiple fronts. Fields enhanced by gravitational lensing boost the odds of detecting faint, distant objects, while statistical methods help identify candidates. Cross-analysis using instruments like Webb and ALMA strengthens detection by combining infrared and sub-millimeter signals. A major challenge is distinguishing between a single population 3 star and a small cluster of low metallicity stars. Current resolution allows detailed analysis, but often not enough to isolate individual stars at such extreme distances. Future missions with even better angular resolution may help overcome this limitation. Webb's data are also being compared to galaxies at similar redshifts. Some have shown comparable patterns, though typically with lower intensity or some chemical contamination. This suggests the object in question may not be unique, but instead part of a larger, still undiscovered population. Ongoing analysis aims to determine whether the signals truly come from pure stars formed shortly after the cosmic microwave background decoupled. If so, this would offer an unprecedented look into the conditions of the universe just tens of millions of years after the Big Bang, when light first emerged from the darkness. Galaxy mergers are a central driver of large-scale cosmic structure formation. Until the James Webb Space Telescope, details of these events during the universe's earliest epochs remained elusive. Now, with its groundbreaking infrared resolution, Webb has revealed mergers between galaxies occurring less than a billion years after the Big Bang. These images showcase dynamic interactions between young structures with complex morphologies and intense star-forming zones. One striking example involves two compact galaxies converging with warped arms, bridges of ionized gas, and extensive dust regions. The intensity of infrared light signals recent violent star formation, at rates far higher than those in isolated galaxies from the same era. These starburst zones are clear indicators of active collisions. Webb's ability to see through dust allows precise mapping of gas and star distribution. Unlike optical telescopes, which are hindered by interstellar opacity, Webb reveals the internal structure of colliding galactic cores, including newly formed stellar clusters and filaments of redistributed material. These mergers also show how dark matter halos interact and merge, accelerating the coalescence of galaxies. Gravitational analyses of internal movements suggest these interactions are driven by massive forces that reorganize stellar and gaseous content, directly influencing the long-term formation of structures like elliptical galaxies. Some images capture galaxies that have already completed their merger phase, but still retain visual remnants of the event, such as asymmetric arms, tidal tails, and deformed central disks. These features help build a timeline of the merger process, pinpointing when peak disruption occurred and how it affected star formation patterns. The MRII, or mid-infrared instrument, captured emissions from polycyclic aromatic hydrocarbons, molecules that form in regions exposed to intense radiation. This indicates that mergers not only reshape galactic structure, but also transform the chemistry of the interstellar medium. These molecules play a role in gas cooling and subsequent star formation. Another notable aspect is the presence of active black holes at the centers of some merging galaxies. The influx of material into galactic cores may fuel their growth. The energy released, a process known as feedback, can regulate or even suppress surrounding star formation, significantly impacting the galaxy's evolutionary path. These early mergers show that the young universe already displayed a surprising level of structural complexity. Instead of small galaxies gradually merging over billions of years, Webb has found evidence of dramatic, large-scale collisions occurring soon after the cosmic dawn. This challenges existing timelines and triggers for galactic growth. Spectral data has enabled measurements of the relative velocities between galactic nuclei, often exceeding hundreds of kilometers per second. These metrics help predict the time remaining until full merger and estimate the kinematic impact on the surrounding intergalactic medium. Computational models are being updated in response. Previous simulations, based largely on Hubble data, predicted mergers would peak later in cosmic history. Now, new parameters suggest the peak may have occurred earlier and more frequently than previously thought. Observing multiple systems at different stages of merging allows researchers to compare environmental conditions, star formation rates, and resulting morphologies. This statistical approach enhances our understanding of how mergers contribute to the rich morphological diversity seen in today's universe. Ongoing analysis continues to focus on mapping the relationship between galaxy mergers, star formation, and central black hole growth. Taken together, these variables offer a more refined picture of how galaxies form, evolve, and interact in the expanding cosmos. Cosmic collisions, dust and gas dancing in primordial galaxy crashes. The James Webb Space Telescope has revealed galaxy collisions in their early stages, occurring less than a billion years after the Big Bang. These events were previously inaccessible due to limitations in resolution and wavelength. Now, with its infrared capabilities, Webb exposes the internal structure of interacting galaxies, including dust lanes, gas streams, and disrupted stellar arms. These collisions are more chaotic and energetic than those observed in the local universe. In several of these systems, massive clouds of gas and dust are seen twisting between the colliding galaxies. This material forms bridges and tidal tails, shaped by gravitational forces acting over millions of light-years. Webb's NIRCam and MIRI instruments detect the glow of star-forming regions within these filaments. The increased density and compression trigger starburst activity, with formation rates far above typical levels. The infrared spectrum also reveals polycyclic aromatic hydrocarbons, molecules that form in intense radiation fields. These complex molecules indicate the presence of massive, young stars heating surrounding dust. The chemical evolution of these regions is shaped by the collision itself, redistributing metals and triggering new cycles of star formation. This provides a unique window into the interplay between dynamics and chemistry. The relative velocities of the galaxies involved often exceed several hundred kilometers per second. These speeds, combined with gravitational interactions, distort the morphology of each system. Disks become warped, nuclei shift, and gas reservoirs are violently disturbed. The Webb telescope tracks these distortions, allowing researchers to reconstruct the geometry and timing of the collision. In some systems, multiple galaxies are merging simultaneously in what's known as a compact group. This scenario leads to even more intense gravitational interactions and may result in the formation of a single, massive, elliptical galaxy. The data gathered by Webb offers insight into how such mergers contribute to the population of large, spheroidal galaxies observed in the present-day universe. Feedback from supernovae and black hole accretion can alter the environment further. The energy released during these processes heats the surrounding gas, potentially quenching future star formation. Webb observes this by detecting emission lines from ionized elements like oxygen and sulfur, which trace the thermal history of the intergalactic medium in and around the colliding systems. Not all the gas is used to make stars. Some is stripped away, forming long tails that drift into intergalactic space. These streams may seed new dwarf galaxies or enrich the cosmic web with metals. Webb's sensitivity allows astronomers to trace these faint features far beyond the limits of previous telescopes. Their morphology provides clues about the direction and intensity of the encounter. The presence of dual-active galactic nuclei in some mergers suggests that black holes are growing simultaneously in both galaxies. As the merger progresses, these nuclei may eventually coalesce into a single, more massive black hole. The dynamics of this process are key to understanding the relationship between galaxy growth and supermassive black hole formation. Webb's observations challenge previous models that assumed most early galaxies were isolated or formed gradually. Instead, many appeared to be part of a turbulent, interactive network of structures. Collisions in the early universe may have been more common than previously thought, accelerating the evolution of galaxies and their environments. Computer simulations are being refined to incorporate these new findings. Parameters like gas density, merger frequency, and angular momentum are being adjusted to match the complexity observed. These simulations will help predict which types of galaxies result from different kinds of collisions and how long the transformation process takes. By comparing systems at different stages, before, during, and after merger, scientists can build a clearer picture of the long-term outcomes. Morphological transitions, chemical enrichment, and the emergence of new structures are all traced in detail. Webb's ability to observe in the mid-infrared is particularly useful for studying obscured cores and heavily dust-enshrouded regions. The results highlight that, Even in the early universe, galactic structures were not static or isolated. They were shaped by motion, collision, and gravitational interaction, all of which left visible imprints in the form of distorted shapes, glowing bridges, and molecular signatures across vast cosmic distances. Cosmic clusters like Pandora, revealing hundreds of galaxies in a single frame. The Pandora cluster, also known as Abell 2744, is a massive collision of 4 smaller galaxy clusters. Observed by the James Webb Telescope, this structure serves as a gravitational lens that magnifies galaxies far behind it. Using this lensing effect, Webb captured an ultra-deep image containing thousands of galaxies in various stages of evolution. The level of detail achieved surpasses anything previously seen at this scale. The cluster's immense gravitational field bends and distorts light from background galaxies, creating arcs, multiple images, and even Einstein rings. These lensing features allow astronomers to study galaxies that would otherwise be too faint or distant to observe directly. Some of the magnified galaxies are seen as they were just 500 million years after the Big Bang, offering rare access to early cosmic history. Webb's image of Pandora combines multiple pointings and filters to cover a wide field of view. The resulting mosaic includes bright, nearby galaxies in the foreground and extremely red-shifted galaxies in the background. This layering of time and distance makes it possible to observe the assembly of cosmic structure across different epochs in one composite scene. The mid-infrared data from MIRI reveals dust-enshrouded star formation in many of the background galaxies. These galaxies are often invisible in optical wavelengths, but glow brightly in infrared due to warm dust heated by young stars. Observing this allows astronomers to estimate star formation rates and determine how galaxies were growing in the early universe. The Pandora field is not just a collection of galaxies, it is also a laboratory for dark matter. By mapping the distortions in light caused by lensing, researchers can infer the distribution of unseen mass throughout the cluster. This helps constrain models of dark matter and its role in structuring the cosmos on large scales. In some regions, multiple lensing effects overlap, amplifying certain background galaxies by factors of 10 to 100. This natural magnification enables high-resolution studies of galaxies that otherwise would be far too dim. Features such as clumpy star formation, spiral arms, and even potential companion galaxies become visible. The image also captures dynamic processes within the cluster itself. Hot gas between the merging subclusters emits X-rays and influences the motion of galaxies through pressure and drag. While Webb does not observe in X-rays, its infrared data complements observations from Chandra and XMM Newton, building a multi-wavelength view of the environment. Gravitational lensing also stretches the light of background galaxies across multiple paths, allowing astronomers to observe the same object from different angles and time delays. This can reveal subtle changes in brightness and shape, and help test predictions of general relativity under extreme conditions. The complexity of the Pandora cluster offers a unique data set for machine learning techniques. Algorithms are being trained to identify lensing features automatically, speeding up the search for rare or extreme galaxies. The volume of data generated by Webb makes such automated tools increasingly valuable for discovery. Spectroscopic data from NIRSpec provides redshift measurements for dozens of galaxies in the field, confirming their distances and clustering behavior. This helps build a three-dimensional map of the area, distinguishing between true cluster members, foreground galaxies, and lensed background systems. Some of the background galaxies identified through Pandora's lensing are among the most distant ever observed. Their light has been stretched across billions of years, and their structure offers clues about early star formation, morphology, and chemical composition. These data points refine models of cosmic evolution. The Pandora cluster illustrates how gravitational lensing and infrared imaging work together to reveal layers of the universe otherwise hidden. The depth, richness, and diversity of the field mark it as one of Webb's most ambitious and revealing observations to date. A perfect Einstein ring around a distant galaxy. One of the most visually striking phenomena captured by the James Webb Telescope is the Einstein ring, a complete circle of light formed by the bending of light around a massive object. In one observation, Webb revealed a nearly perfect ring created by the lensing of a background galaxy by a foreground elliptical galaxy. This alignment is rare and offers a precise natural laboratory for gravitational lensing physics. The ring was detected in a system known as SPT-SJ0418394751.8, where a distant galaxy's light is wrapped around the mass of a closer galaxy, forming a full circle. The symmetry of the structure indicates a high degree of alignment between the observer, the lens, and the background source. Such precision enables extremely accurate measurements of mass distribution in the lensing galaxy. Spectroscopic analysis confirms that the light forming the ring comes from a galaxy billions of light-years farther than the lens. The curvature and intensity of the ring provide data on how the light has been distorted, which in turn allows astronomers to model the gravitational field of the foreground object. Webb's resolution makes this possible at levels not achieved with previous instruments. In this case, the background galaxy is being magnified by a factor of several times, allowing researchers to resolve details within it that would otherwise be undetectable. The lens acts as a cosmic magnifying glass, offering a view into a galaxy that may have existed just a few 100 million years after the Big Bang. Such resolution is critical for studying star formation and structure in the early universe. The shape of the ring also helps determine the lensing galaxy's dark matter profile. Since dark matter contributes to the gravitational bending of light, any irregularities in the ring can hint at substructure within the lens. The smoothness of the ring in this observation suggests a well-distributed dark matter halo without large clumps. Webb's near-infrared capabilities allow it to capture these lensing events even when the background source is heavily redshifted. This expands the catalog of known Einstein rings to higher redshifts, revealing galaxies that were previously beyond the detection limits of optical telescopes. The red color of the ring confirms that the background galaxy lies deep in the early universe. Multiple instruments onboard Webb contribute to the analysis. NIR-CAM provides high-resolution imaging of the ring's structure, while NIR-SPEC gathers spectroscopic data to determine redshifts and velocity distributions. The combination allows for precise modeling of the geometry and internal dynamics of both the lensing and background galaxies. In some frames, the ring appears slightly elongated or asymmetrical. These variations are not artifacts, but reflect real differences in mass concentration, either in the lens or along the light path. By mapping these distortions, astronomers can infer the presence of otherwise invisible subhalos or filamentary structures. The brightness of the ring varies around its circumference, revealing differences in the magnification factor at each point. These fluctuations are used to trace small gravitational perturbations that influence how the light is bent. In well-aligned systems like this one, the detail is high enough to build pixel-by-pixel lensing maps. This kind of observation also aids in refining cosmological parameters. By comparing the apparent and actual positions of the background galaxy's components, researchers can extract data relevant to the Hubble constant and matter density in the universe. Such rings act as calibrators for large-scale cosmic measurements. Webb's sensitivity opens the door to detecting even fainter rings around smaller or more distant systems. Some candidates are being evaluated for partial rings or arcs that indicate incomplete lensing events. These partial structures still offer valuable data for gravitational modeling, particularly when observed from multiple angles. The Einstein ring observed by Webb provides a clean, well-resolved example of gravitational lensing in action. It captures both the geometry of space-time distortion and the practical effects of magnifying ancient light, enabling direct study of galaxies that would otherwise remain hidden. Why seeing the universe in infrared changes everything we knew about the past. Most of what we observe from distant objects has traveled for billions of years before reaching us. As the universe expands, that light is stretched. Its wavelength increases, shifting it into the infrared part of the spectrum. Optical telescopes miss much of this light, especially from the earliest galaxies. That's where the James Webb Telescope becomes essential. By observing in infrared, Webb captures light that has been redshifted beyond the reach of visible light instruments. This includes emissions from stars, galaxies, and dust clouds that formed when the universe was only a few 100 million years old. Infrared observation enables access to these early epochs in a way that simply wasn't possible before. The telescope's instruments are tuned to detect near and mid-infrared wavelengths, revealing objects obscured by dust or too faint to be seen otherwise. Star-forming regions within dense molecular clouds become visible, as do galaxies at redshifts above 10. This access to obscured and distant environments fundamentally shifts our understanding of cosmic evolution. In many cases, galaxies that appeared as faint smudges in Hubble images are revealed in Webb data to be complex, structured systems. Disks, clumps, and even spiral features are now visible where before there was only blurred light. This changes how we classify early galaxies and redefines when and how structure emerged in the universe. Infrared imaging also uncovers the chemical fingerprints of celestial objects. Through spectroscopy, elements like carbon, oxygen, and water vapor can be identified in galaxies and exoplanet atmospheres. These signals are strongest in the infrared, especially in the early universe, where even high-energy events emit radiation that has since redshifted beyond visible detection. Dust plays a major role in hiding early stars and galaxies from view. In the optical range, this dust blocks light almost completely. Infrared wavelengths pass through it, allowing us to peer into star nurseries and galactic cores. This capability provides insights into how galaxies assembled their mass and formed new generations of stars. Webb's ability to detect faint infrared light also impacts our knowledge of galaxy formation timelines. Many galaxies now identified at redshifts greater than 10 appear more massive and evolved than expected. These findings suggest that star formation began earlier and proceeded more efficiently than models had predicted. Regions once considered voids or dark spots in older sky surveys are now teeming with galaxies. Some of these galaxies are compact and extremely red, traits that imply they are both old, in cosmic terms, and heavily redshifted. The infrared view reshapes the map of the universe's early structure, adding depth where there was once apparent emptiness. Instruments like NIRCam and MIRI are key to this transformation. NIRCam captures high-resolution images in short infrared bands, revealing galaxy morphology and star cluster distribution. MIRI extends this into longer wavelengths, showing warm dust and molecular emissions even in the most distant galaxies Webb can reach. Comparisons between infrared and optical data highlight how much was previously missed. Galaxies undetected by Hubble now dominate certain regions in Webb's deep fields. This shift in visibility influences theories on cosmic reionization and the timeline of stellar population growth in the first billion years. Infrared observations also challenge assumptions about cosmic temperature, star brightness, and the behavior of matter under early universe conditions. The properties of infrared emission help refine models of stellar atmospheres, galaxy cooling, and the composition of interstellar dust across time. The data from Webb's infrared view doesn't replace what was known from optical astronomy. It extends it. By adding a new dimension to our view of cosmic history, infrared light allows scientists to reconstruct the early universe with greater completeness, resolution, and context than ever before. How scientists turn Webb's invisible data into visible, colorful images. The James Webb Space Telescope captures data in wavelengths the human eye cannot see, primarily near and mid-infrared light. These signals arrive at Earth as digital information, arrays of numerical values representing light intensity at various infrared wavelengths. To create images, scientists must convert these data into visual formats that can be interpreted by the public and researchers alike. Each observation is first processed through calibration pipelines that correct for instrumental noise, cosmic rays, and thermal effects. The raw signal is then separated by wavelength, allowing scientists to assign specific infrared bands to colors visible to the human eye. This mapping is not arbitrary. It preserves the physical structure and intensity distribution of the original source. Typically, shorter infrared wavelengths are assigned to blue or green, while longer ones are mapped to red or orange. This technique, called chromatic ordering, provides a consistent logic for translating wavelengths outside human perception into color-coded representations. It helps highlight temperature differences, gas structures, and star-forming regions with clarity. These images are not intended to be false or decorative. They are scientifically accurate visualizations of real data, constructed to reveal structures that would otherwise remain abstract in numeric form. In many cases, multiple filters are combined into composite images, allowing subtle features to emerge that would be invisible in monochromatic views. The process also involves aligning the different exposures and correcting for optical distortions. Because Webb captures light at various focal depths and field angles, data from different instruments or filters may not overlap perfectly. Image processing teams at institutions like STCSI perform precise registration to ensure alignment and fidelity. In regions with strong signal variation, additional techniques like contrast stretching and tone mapping are applied. These methods enhance visibility without distorting the underlying scientific information. Care is taken to avoid introducing visual artifacts that might mislead interpretation or exaggerate certain features. The result is not just a visual product, but a tool for scientific discovery. By assigning colors to specific molecular emissions or temperature zones, scientists can visually differentiate between hot stars, cooler dust, and various ionized gases. This separation allows for immediate spatial analysis of astrophysical processes within galaxies and nebulae. Color assignments are often guided by known spectral lines. For instance, hydrogen alpha emission may be mapped to red, while molecular emissions from dust may appear in green or orange, depending on wavelength. These choices enhance interpretability for researchers while also producing visually compelling imagery. Some datasets are used purely for analysis and never translated into color images. However, when shared with the public, these processed visuals help bridge the gap between raw infrared data and human experience. The images serve both educational and research purposes, uniting scientific rigor with visual accessibility. Webb's imaging team frequently collaborates with artists and data visualization experts to refine the presentation of these scenes. While preserving scientific accuracy, they consider balance, symmetry, and color harmony to make the images intuitive and aesthetically engaging. The goal is clarity, not embellishment. The final images are often released alongside scientific papers, with documentation detailing filter use, color mapping, and processing steps. This transparency ensures reproducibility and helps prevent misinterpretation. Researchers worldwide can then compare, reprocess, or analyze the data with confidence. What the public sees in these colorful views of the cosmos is more than an artistic rendering. It's the translation of invisible light into meaningful form, crafted through layers of physical measurement, mathematical processing, and careful interpretation. How Webb's foldable mirror was engineered to fit inside a rocket and unfold in space. The James Webb Space Telescope's primary mirror spans 6.5 meters in diameter, too large to fit inside any existing rocket fairing. To overcome this limitation, engineers designed the mirror to fold like a three-panel wing, allowing it to stow compactly during launch. Once in space, the mirror unfolds through a precise multi-step deployment sequence lasting nearly 2 weeks. The mirror is made of 18 hexagonal segments coated with a thin layer of gold to enhance infrared reflectivity. These segments are mounted on a deployable structure that allows for both folding and fine adjustment. The central panel remains fixed during launch, while the side panels are latched into position and later released for extension. The deployment sequence begins only after Webb reaches its operational orbit near the second Lagrange point, L2, 1.5 million kilometers from Earth. This timing ensures that any mechanical issue won't threaten launch success or spacecraft stability. The process involves motorized hinges, tension cables, and locking mechanisms that guide the panels into their full configuration. Each segment is also equipped with actuators capable of nanometer-scale positioning. Once deployed, these actuators align the mirror segments so precisely that the entire structure behaves like a single optical surface. This alignment is critical for achieving the sharp resolution necessary for high-precision infrared observations. The complexity of the deployment led engineers to design extensive ground testing. Simulations, vibration tests, and cryogenic trials were conducted to ensure that each mechanism would perform reliably in the vacuum of space. Webb's deployment system includes 344 single points of failure, each one a potential risk if not flawlessly executed. Thermal control is another essential part of the design. The mirror must remain at cryogenic temperatures to avoid emitting infrared radiation that would interfere with observations. To support this, the deployment of the mirror is synchronized with the unfolding of the 5-layer sun shield, which blocks solar heat and maintains low operational temperatures. Material selection played a key role. The mirror segments are made from beryllium, chosen for its light weight, strength, and stability at extremely low temperatures. This metal minimizes deformation and maintains its shape across wide thermal gradients, preserving optical performance in space. Engineers also designed the unfolding to be reversible in simulation, though not in orbit. During testing, each hinge and motor was verified for function, durability, and response to contingencies. Redundant sensors and real-time telemetry were built into the system to monitor every step of the deployment. The alignment process took several months after unfolding. Each mirror segment had to be adjusted through a calibration routine using observations of a bright reference star. Images from each segment were analyzed and used to bring the segments into sharp coherence, forming a single functional optical system. The entire architecture of the telescope was built around this foldable mirror concept. Other components, such as the instrument module and sunshield, were also designed to fold and deploy in sequence. This interdependence added layers of complexity, requiring coordination across multiple systems and software layers. Despite its challenges, the mirror deployment was executed flawlessly in early 2022, marking one of the most complex mechanical operations ever performed in space. Its success validated decades of engineering effort and enabled Webb to begin its science mission with full optical capability. What Webb sees today, distant galaxies, ancient light, and invisible chemistry, would not be possible without this mechanical ingenuity. The foldable mirror transformed the constraints of launch into an unprecedented window into deep space. Why the James Webb was sent 1.5 million kilometers from Earth, and what happens there. Unlike telescopes in low Earth orbit, the James Webb Space Telescope was placed at a far more distant location, the second Lagrange point, or L2, approximately 1.5 million kilometers from Earth. This gravitationally stable point allows Webb to maintain a fixed position relative to both Earth and the Sun. It's not a spot of stillness, but a dynamic orbit that balances gravitational forces in a precise configuration. Positioning Webb at L2 offers key advantages for thermal and observational performance. The telescope must remain extremely cold to detect faint infrared signals from distant galaxies. By staying in line with Earth and the Sun, Webb can use its sunshield to block both sources of heat simultaneously. This orientation would be impossible to maintain in closer orbits. The 5-layer sunshield is always kept facing the Sun, while the telescope's instruments point in the opposite direction, toward deep space. This thermal shielding allows the instruments to cool below 50 Kelvin, minimizing their own infrared emission. Without this level of insulation, Webb's detectors would be overwhelmed by their own heat. The L2 orbit also minimizes interruptions in observation. Because Earth, the Moon, and the Sun all remain on the same side of the telescope, Webb can keep its field of view continuously directed toward the cosmos. It's able to observe for weeks at a time without needing to reorient or hide behind planetary bodies, unlike low-orbit telescopes. The stability of L2 is not perfect, so Webb actually orbits around it in what's called a halo orbit, tracing a gentle ellipse that keeps it in constant sunlight while allowing its solar panels to maintain power. This orbit is dynamically maintained with periodic course corrections using onboard thrusters. Communication with Earth is maintained through the Deep Space Network, which provides nearly continuous contact for data transmission and command uploads. The fixed geometry of the L2 orbit helps keep antenna alignment stable, reducing the complexity of maintaining long-distance communication. Another benefit of being so far from Earth is the reduction of infrared background noise from our planet and its atmosphere. Even at high altitudes, Earth radiates heat that could interfere with sensitive infrared measurements. By operating at L2, Webb avoids this thermal contamination and achieves better signal clarity. L2 also offers protection from reflected light. Earthshine and moonlight, which can affect optical and infrared telescopes closer to home, are effectively shielded by the sunshade at this distance. This creates a dark, stable platform for observing the faintest signals from early galaxies and exoplanet atmospheres. The trade-off for this location is that Webb cannot be serviced. Unlike the Hubble Space Telescope, which was visited multiple times by astronauts, Webb's distance makes physical maintenance impossible. Its systems had to be designed with high redundancy, extreme reliability, and autonomous correction capabilities. Deployments and calibrations at L2 had to be executed without human intervention. Every mechanism, from mirror unfolding to instrument alignment, was performed remotely, relying on automated sequences and real-time feedback from the spacecraft. The margin for error was narrow, and pre-launch testing was extensive. Webb's location at L2 also affects mission duration. It carries a limited supply of fuel for maintaining its position and orientation. Mission planners expect the supply to last for at least 10 years, depending on maneuver efficiency and thermal stability over time. The choice of L2 is not simply a matter of distance, but of environmental optimization. It provides the conditions necessary for infrared astronomy at a level of sensitivity and precision that cannot be matched from Earth or near-Earth space. How Webb is changing our understanding of time, space, and cosmic origin. The James Webb Space Telescope was designed to observe the earliest light in the universe, targeting galaxies formed just a few 100 million years after the Big Bang. What it has revealed so far suggests that our timeline of cosmic evolution may need revision. Galaxies appear more massive, more structured, and more chemically enriched than expected for such early epochs. This challenges long-standing models of structure formation, which proposed a gradual buildup of galaxies through hierarchical merging over billions of years. Instead, Webb's data show that some galaxies reached complex maturity in a fraction of that time. Their morphology, metallicity, and stellar populations reflect conditions once thought impossible in the universe's first billion years. Time itself becomes less intuitive under these findings. If massive galaxies and active black holes were already in place shortly after reionization, the mechanisms that drove cosmic evolution must have been far more efficient. The distinction between early and late becomes blurred when key structures appear so soon after the Big Bang. Space, too, is being redefined. Infrared images from Webb reveal a cosmos more densely populated and dynamic than previous surveys suggested. Where other telescopes saw voids or faint signals, Webb detects clusters, filaments, and active star-forming regions. The map of the early universe now includes structure and complexity at unexpected scales. The observation of chemical elements like carbon and oxygen in young galaxies suggests multiple cycles of star formation had already occurred. This implies the presence of earlier generations of stars, perhaps even the elusive population 3 stars, playing a role in shaping the visible universe more quickly than anticipated. Instruments like NRCam and NRSpec enable detailed spectral analysis of these galaxies, measuring redshift, metallicity, and stellar content. The resulting data support revised models of early starburst behavior, faster gas cooling, and more intense gravitational clustering than previously assumed in standard cosmology. These findings ripple into broader questions about cosmic inflation, dark matter, and dark energy. If the early universe was capable of forming massive structures this quickly, theoretical frameworks may need adjustment to account for the observed acceleration of growth. This could refine our understanding of how expansion interacted with matter distribution over time. The traditional narrative of a smooth transition from simplicity to complexity is giving way to a more abrupt emergence of structure. The presence of spiral galaxies, starburst systems, and merger activity at redshifts greater than 10 suggests that dynamic processes were already underway when the universe was less than 500 million years old. Webb's ability to probe deep into time makes these changes visible in ways not previously possible. Instead of inferring conditions from nearby analogs or cosmic microwave background data alone, astronomers can now directly observe the developmental stages of the earliest cosmic objects. This observational reach adds detail and correction to theoretical models. The way we define cosmic origins is also shifting. Rather than pinpointing a moment of first light or the formation of the first galaxy, Webb's observations suggest a complex continuum of events happening in parallel across large spatial volumes. Multiple sites of early structure appear to have developed simultaneously, not sequentially. These revisions don't erase previous knowledge, but expand its context. The structure and content of space-time remain governed by known physics, but the parameters shaping early evolution are proving more flexible and diverse than anticipated. What changes is not the foundation, but the timeline and texture of what followed. Carbon, water vapor, and CO2 detected in the atmosphere of an exoplanet. One of James Webb's landmark capabilities is its ability to perform transmission spectroscopy on exoplanets. By observing a planet as it transits in front of its star, the telescope captures how starlight filters through the planet's atmosphere. In one such observation, Webb revealed clear signs of carbon dioxide, water vapor, and carbon-based molecules in the atmosphere of the hot gas giant WASP-39b. The planet orbits a star about 700 light-years from Earth and has been studied before, but never with this level of precision. Webb's NIR-SPEC instrument detected subtle absorption features at specific infrared wavelengths. These dips in light intensity match the fingerprints of CO2, H2O, and traces of other carbon-bearing compounds, offering the most detailed chemical map of an exoplanet atmosphere to date. Water vapor was confirmed across a broad range of the infrared spectrum, indicating not just the presence of H2O, but its distribution at different altitudes. This allows scientists to infer the temperature profile and vertical structure of the atmosphere. The presence of water also suggests a possible formation history rich in icy material beyond the system's original frost line. Carbon dioxide appears as a strong feature near 4.3 microns. Its detection provides key constraints on the planet's atmospheric composition and internal processes. CO2 is a valuable tracer for understanding the balance between hydrogen, oxygen, and carbon, elements that affect not just climate, but the origin and migration of the planet itself. In addition to water and CO2, carbon monoxide and traces of sulfur dioxide may also be present. These molecules are consistent with photochemical reactions triggered by high-energy radiation from the host star. Such reactions can create hazes and secondary molecules in the upper atmosphere, shaping its optical properties. The spectrum shows no sign of a flat baseline, meaning the atmosphere is not dominated by thick, featureless clouds. Instead, it appears clear enough to allow light to pass through various gas layers. This transparency enables direct probing of pressure and temperature gradients, enhancing our understanding of heat circulation and atmospheric dynamics. Webb's data suggest a non-uniform atmosphere, possibly with regions of upwelling gases and localized temperature variations. These findings are consistent with 3D circulation models of hot Jupiters, where intense stellar irradiation causes complex day-night patterns and rapid winds across the terminator line. The chemical balance of the atmosphere indicates that the planet likely formed farther from its current orbit and migrated inward over time. This migration would explain the presence of volatiles like water and carbon compounds originally collected in the cooler outer regions of the protoplanetary disk. These results mark the first unambiguous detection of CO2 in an exoplanet atmosphere, opening the door to comparative studies with other planetary types. Future observations will explore how common such compositions are and how they vary with planet size, temperature, and stellar environment. The high precision of Webb's instruments also sets the stage for detecting biosignature gases in smaller rocky planets. While WASP-39b is not a candidate for life, the techniques refined here will be used to analyze more Earth-like worlds in the coming years. The search for habitable atmospheres begins with learning to read the chemistry of giants. Each molecule detected tells a part of the planet's story, how it formed, how it evolved, and how it interacts with its star. Webb's spectral sensitivity transforms these distant worlds from points of light into chemically active systems, expanding our view of planetary diversity. The super-Earth GJ1214b and its dense, layered atmosphere. GJ1214b is a super-Earth located about 48 light-years away, orbiting a cool red dwarf star. It has long intrigued astronomers due to its intermediate size, larger than Earth but smaller than Neptune. Until recently, its atmosphere remained largely mysterious. Now, with the James Webb Telescope, scientists have gained the first detailed look at its atmospheric composition and structure. Using the MIRI instrument, Webb observed GJ1214b as it passed in front of its star. Unlike previous instruments, MIRI captures mid-infrared light, allowing scientists to peer deeper into the planet's atmosphere. The resulting data revealed a complex, multi-layered atmosphere with a strong absorption feature from water vapor and signs of methane or other carbon-rich molecules. One of the most surprising findings was the planet's brightness temperature, which changes significantly depending on the wavelength observed. This indicates a stratified atmosphere, where different gases dominate at different altitudes. These layers likely interact through vertical mixing, influenced by the planet's strong gravity and potential tidal locking. The planet appears to be enveloped in a thick blanket of haze or aerosols. This haze scatters light in a way that makes the transmission spectrum relatively featureless at shorter wavelengths. However, Webb's infrared observations bypass this limitation, revealing chemical fingerprints that had remained hidden from optical telescopes. Water vapor is a dominant component in the observable spectrum, but it's mixed with carbon-bearing compounds, possibly including methane and hydrogen cyanide. These molecules suggest an atmosphere that may have formed in a volatile-rich environment, or one shaped by photochemical reactions driven by stellar UV radiation. GJ1214b's atmosphere may also be influenced by internal heat. The lack of extreme temperature contrast between the planet's day and night sides implies some degree of energy redistribution. Atmospheric circulation models suggest winds and convection could be transporting heat across the terminator region, smoothing out thermal differences. The planet's mass and radius indicate a substantial atmosphere relative to its size. This suggests that GJ1214b did not lose its envelope during formation, possibly protected by a strong magnetic field or formed in a quiet, low-radiation zone. Its ability to retain such a dense atmosphere makes it an ideal candidate for further climate and evolution modeling. Webb's observations help rule out the possibility that the atmosphere is composed entirely of hydrogen and helium. Instead, the presence of heavier molecules point to a more complex, enriched composition. This has implications for planet formation theories, especially those involving mini-Neptunes and water worlds. The clarity of the data also provides constraints on the planet's albedo and emissivity. These parameters influence how much stellar energy is absorbed versus reflected, affecting surface conditions and potential atmospheric escape. Understanding this balance is key to modeling long-term planetary stability. While GJ1214b is likely too hot and volatile-rich to be habitable, it serves as a bridge between rocky planets and gas giants. Studying it helps refine classification systems and offers a testing ground for models that will eventually be applied to terrestrial exoplanets. Its status as a super-Earth makes it especially valuable in comparative planetology. The techniques used to analyze GJ1214b will be applied to a growing list of transiting exoplanets in Webb's queue. Each observation refines our understanding of atmospheric diversity, formation history, and chemical evolution in planetary systems. GJ1214b now stands as one of the most thoroughly characterized non-Earth-size planets to date. This planet's atmosphere, layered and rich with volatiles, offers a glimpse into the complexity that awaits in worlds beyond our solar system, an example of how even intermediate-sized planets can host intricate and dynamic climates. Exoplanets with opaque clouds, extreme winds, and unexpected chemistry. Among the exoplanets observed by the James Webb Telescope, several display atmospheres that defy expectations, not because of their clarity, but due to how opaque and dynamic they are. These are mostly hot Jupiters, orbiting close to their stars, where high temperatures and intense radiation drive chaotic weather systems and thick cloud-covered skies. Despite their brightness, these planets are challenging to analyze due to persistent atmospheric hazes. Transmission spectra from these exoplanets often appear flat or featureless, suggesting that clouds or aerosols are blocking much of the light from passing through the atmosphere. These clouds are not made of water, but of exotic compounds, such as silicates, iron, and titanium oxide, which can condense at extremely high temperatures. They form dense layers that obscure spectral features and complicate chemical analysis. In some observations, however, Webb's infrared instruments have managed to peer through parts of these cloud decks. By focusing on longer wavelengths, where scattering is less intense, scientists have detected traces of water vapor, carbon monoxide, and even metal hydrides. These findings suggest that beneath the cloud cover lies a chemically active atmosphere with complex vertical gradients. One planet, WASP-17b, shows spectral evidence of aluminum oxide aerosols and possible sulfide clouds. These particles form in the upper atmosphere and may reflect stellar radiation, altering the planet's thermal balance. The combination of reflection, absorption, and circulation creates conditions far more extreme than anything seen in the solar system. Webb's measurements also indicate extremely high wind speeds, with atmospheric flows reaching several kilometers per second. These winds are likely driven by the intense day-night contrast on tidally locked planets. The resulting jet streams redistribute heat, flatten temperature differences, and generate turbulence across the terminator region. Temperature inversions have also been detected in some of these planets, where the upper atmosphere is hotter than the layers below. This can occur when high-energy stellar radiation is absorbed by molecules like titanium oxide, reversing the typical thermal structure. These inversions impact how infrared light escapes the atmosphere and change the planet's overall emission spectrum. Chemical disequilibrium is another recurring theme. Many of the gases observed, like methane or ammonia, are found in quantities that suggest active mixing or photochemical destruction. In such high-temperature environments, equilibrium chemistry fails to predict observed compositions, forcing researchers to revise their atmospheric models. Webb's ability to detect variations in brightness during secondary eclipses has provided additional insights. These variations help map the dayside thermal profile of these planets, revealing temperature hotspots and possible longitudinal asymmetries in cloud coverage. Combined with phase curve data, this builds a more three-dimensional view of the atmosphere. Some planets also exhibit unusual albedo properties. Despite their proximity to bright stars, they reflect very little light, suggesting either strong absorption by atmospheric molecules or surfaces blanketed by dark, heat-trapping clouds. Understanding this low reflectivity helps explain the planet's internal temperatures and energy redistribution. Not all signals are fully understood. Some exoplanets show unexpected absorption features that don't match known molecular spectra. These may hint at new chemical pathways or exotic compounds not yet included in atmospheric models. Ongoing observations and lab-based spectroscopy aim to close these gaps. These findings broaden our view of what planetary atmospheres can be. They reveal environments that are dynamic, hostile, and chemically diverse, operating under physics that diverge from solar system norms. Each planet adds complexity to the growing library of atmospheric behaviors. Opaque clouds, fierce winds, and exotic chemistry highlight the extremes of planetary weather. Far from being uniform or predictable, these atmospheres challenge assumptions about planetary structure, offering new parameters to guide future exploration. Turbulent atmospheres in giant planets with surprising signals. Giant exoplanets offer a diverse range of atmospheric behaviors, and Webb's observations have uncovered turbulence, chemistry, and thermodynamics not predicted by previous models. These planets, especially the hot Jupiters and warm Neptunes, exhibit atmospheric structures driven by intense irradiation, rapid rotation, and non-equilibrium processes. One of the key surprises is the presence of broad asymmetric absorption features in transmission spectra. These features suggest stratified atmospheres with varying temperature, pressure, and composition, depending on altitude and location. Webb's high-resolution data has revealed that these layers interact in complex ways, often leading to unexpected distributions of key molecules. For example, the detection of carbon monoxide and water vapor together in specific ratios suggests vertical mixing, where hot gases from deeper layers are brought to the upper atmosphere. This upwelling can also transport refractory elements like sodium and potassium, influencing both the thermal profile and the planet's reflective properties. Some of these planets exhibit extreme temperature differences between their day and night sides, sometimes exceeding 1,000 degrees Celsius. This disparity drives powerful atmospheric circulation patterns, including supersonic jet streams and standing waves across the equator. These features distort spectral lines and contribute to temporal variability in observed signals. Webb's phase curve observations track how brightness changes as the planet orbits its star. In several cases, the curve is skewed, indicating heat is not distributed evenly. The offset in peak brightness reveals that winds shift thermal energy away from the substellar point, creating complex flow regimes that differ from those modeled with static atmospheres. Cloud formation appears to be both widespread and highly variable. In planets like WASP-43b and HAT-P7b, clouds of manganese sulfide or silicate grains form on the cooler night side and are destroyed on the hot day side. This cycle of condensation and evaporation adds a dynamic element to the vertical structure of the atmosphere. Temperature inversions, once thought rare, have now been confirmed in multiple giant exoplanets. These inversions are driven by the absorption of stellar UV and visible radiation in the upper atmosphere. Molecules such as vanadium oxide and titanium oxide play roles in this energy capture, leading to heating above the cloud tops. Unexpected chemical species continue to appear in Webb's spectra. Traces of sulfur dioxide, hydrogen cyanide, and even hints of phosphine have emerged in various planets. These molecules often require specific temperature and pressure conditions to form, pointing to localized chemistry shaped by dynamic atmospheric processes. Spectral signatures also vary with time. Repeated observations of the same planet have shown changes in emission profiles, possibly due to evolving weather patterns or shifts in cloud distribution. These findings suggest that some exoplanet atmospheres are not only extreme, but also temporally unstable. Energy balance calculations based on observed fluxes reveal inefficiencies in how some planets radiate heat. This may be due to deep atmospheric layers retaining thermal energy, or to unknown absorbers altering the expected emission spectrum. Webb's data allow researchers to fine-tune radiative transfer models and test new hypotheses. Polar regions may host entirely different atmospheric conditions. Although not directly observable with current instruments, inferred signals from light curves suggest cooler, possibly cloudier zones at high latitudes. This introduces latitudinal variation into models that have traditionally emphasized equatorial dynamics. The study of these turbulent, layered, and chemically rich atmospheres offers a laboratory for testing the boundaries of planetary climate physics. They demonstrate that even within broad categories like gas giant, there is a remarkable range of atmospheric behavior shaped by environment, history, and stellar influence. What emerges is not a unified picture, but a collection of unique climates, each revealing a different pathway through which a planet can evolve and express its atmospheric identity. Titan's true appearance, what Webb reveals about familiar weather on an alien world. Titan, Saturn's largest moon, has long intrigued scientists with its thick atmosphere, methane lakes, and complex organic chemistry, but until recently, even its surface remained mostly hidden. The James Webb Space Telescope, using its infrared capabilities, has penetrated Titan's dense haze to capture the most detailed observations yet of its atmospheric layers and surface activity. These findings provide a sharper view of a world that shares meteorological features with Earth. Using the NIRCam and NIRSpec instruments, Webb observed Titan during optimal viewing periods, allowing scientists to detect reflections from both atmospheric layers and the surface. For the first time, researchers were able to resolve cloud patterns, observe regional weather systems, and detect temporal changes in atmospheric brightness, signs of active weather dynamics. Webb's infrared sensitivity allowed it to identify methane clouds forming in Titan's troposphere. These clouds behave similarly to water clouds on Earth, condensing, drifting, and dissipating over time. Their movement provide insight into wind patterns, thermal gradients, and the seasonal shifts that drive Titan's climate cycles. One observation revealed a large methane cloud system over Titan's northern hemisphere, consistent with the beginning of the Moon's summer. These clouds form as sunlight heats surface reservoirs of methane and ethane, triggering evaporation and cloud formation. The process mirrors Earth's water cycle, but with entirely different compounds. Webb also detected evidence of haze layering in the stratosphere, formed by photochemical reactions triggered by solar UV light. These reactions produce hydrocarbons and nitriles, which accumulate into smog-like layers. The vertical distribution of these hazes affects how heat moves through the atmosphere and influences Titan's overall energy balance. The data showed subtle variations in surface brightness that may correspond to terrain differences, liquid deposits, or moist regions. While Webb cannot resolve features at the same level as radar instruments like those on Cassini, it does offer thermal and chemical contrast between surface zones, helping map temperature and possibly surface composition. Changes observed across multiple sessions suggest a dynamic lower atmosphere. Bright spots appeared and faded in infrared, possibly indicating the formation and dissipation of clouds or haze bursts. These phenomena provide rare opportunities to study climate activity on a moon with an active methane cycle. Titan's temperature profile, as inferred from Webb's measurements, reveals stratification and potential inversion layers. Such features are common in dense atmospheres and influence cloud behavior and wind shear. Understanding these layers gives clues to seasonal and latitudinal climate shifts. Comparisons with Earth's climate models help interpret Titan's weather. Despite differences in chemistry and temperature, both bodies experience evaporation, condensation, cloud formation, and precipitation. This parallel makes Titan a valuable analog for studying atmospheric physics in extreme environments. The observation of complex hydrocarbons, including acetylene and ethane, support models of prebiotic chemistry on Titan's surface and upper atmosphere. These molecules form from methane breakdown and could play roles in surface processes or interactions with Titan's subsurface ocean. Webb's data complement past missions by offering an infrared perspective that was previously limited. Unlike visible light telescopes, which are blocked by Titan's haze, Webb can track deeper layers and capture real-time weather phenomena. Its observations are helping to build a more complete model of Titan's climate system. Titan emerges not as a static, frozen world, but as an active, weather-driven environment with its own version of rain, clouds, and seasonal change. Through Webb's lens, its alien nature becomes a bit more familiar, shaped by cycles that, while chemically different, operate under principles seen closer to home. The Carina Nebula exposed, violent starbirth and shattered pillars. The Carina Nebula, a massive star-forming region about 7,500 light-years from Earth, has long captivated astronomers. With the James Webb Space Telescope, this nebula has been observed in unprecedented detail, revealing a chaotic environment of collapsing gas clouds, shredded dust pillars, and violently forming stars. The images captured by Webb show that the process of stellar birth is more turbulent and sculptural than previously imagined. Webb's INRCam and MIRI instruments reveal sharp contrasts between dense pillars and surrounding cavities. These pillars, often shaped like fingers or ridges, are composed of gas and dust being eroded by intense radiation from nearby massive stars. The ultraviolet light strips electrons from hydrogen atoms, carving out ionized regions and blasting apart weaker structures. One of the most striking features is the visible fragmentation of these dust columns. Rather than solid structures, the pillars appear porous and unstable, with internal voids and filamentary substructure. These details suggest that radiation pressure and stellar winds are actively shredding the clouds from within, triggering star formation while also destroying the environment around it. Embedded within the dust are protostars, some still surrounded by disks of material that may eventually form planetary systems. These young stars emit their own outflows in jets, adding another layer of feedback to the already chaotic region. Webb's infrared vision allows detection of these deeply buried objects, invisible in optical wavelengths. In several zones, shock fronts and bow-shaped structures are seen, marking where stellar winds crash into denser gas pockets. These collisions compress material, which can collapse under gravity and ignite nuclear fusion, forming new stars. This feedback-driven process explains the clustered nature of star formation in regions like Carina. The nebula also features cavities likely carved out by supernovae from previous generations of massive stars. These voids act as cosmic clearing zones, where dust has been swept away and new cycles of collapse can begin. Webb captures temperature differences in these zones, offering clues to their age and formation history. Chemical analysis of the region reveals emissions from polycyclic aromatic hydrocarbons and ionized gas. These compounds trace energetic processes and help identify where UV radiation is strongest. Their distribution outlines the boundaries between active star-forming regions and evacuated zones. The diversity in pillar size, density, and orientation suggests a turbulent origin shaped by both internal gravity and external radiation. In some cases, the tips of the pillars contain multiple protostars, evidence that these dense nodes are prime locations for stellar clustering. Radiative pressure sculpts not only the large structures, but also shapes smaller-scale instabilities. Some wispy tendrils and arcs may be remnants of earlier star formation episodes or traces of collapsing filaments. Webb's high resolution makes it possible to study these features in fine detail, tracing their morphology and thermal properties. The observations also provide insight into the timing of star formation. The varying degrees of erosion and brightness among the pillars imply different stages of evolution. This layered structure allows scientists to reconstruct how star formation propagates across the nebula over time. While telescopes like Hubble revealed the beauty of the Carina Nebula, Webb exposes its underlying dynamics, the interplay of destruction and creation, where radiation simultaneously triggers and disrupts stellar birth, is clearer than ever in these observations. The Carina Nebula, under Webb's gaze, appears as both a nursery and a battlefield, a vast, glowing volume of space where stars are born in violence and sculpt the very clouds from which they emerge. How Webb uncovered hidden structures in seemingly empty nebulae. Before the James Webb Space Telescope, many nebulae were thought to contain large, empty voids, dark regions where gas and dust seemed to thin out completely. These gaps were often interpreted as evidence of exhausted star formation, or as cavities carved out by stellar winds. But Webb's unprecedented infrared sensitivity has revealed that many of these empty zones are far from void. They're filled with faint, cold structures previously invisible to even the best telescopes. One key example comes from observations of the Southern Ring Nebula. Earlier images, including those from Hubble, showed a bright shell of gas surrounding what appeared to be a hollow center. But Webb, operating in the mid-infrared, revealed fine, nested shells of material, concentric arcs, and wispy filaments, structures produced by pulses of gas ejected over thousands of years by the dying star at the center. These internal layers are composed of molecular gas and dust that emit faint infrared light, too subtle to be picked up in visible wavelengths. Webb's instruments, particularly MIRI, can detect heat signatures from these materials, effectively lighting up the dark zones. Each layer corresponds to a phase in the central star's late evolution, allowing astronomers to reconstruct its final centuries in detail. In other planetary nebulae, Webb identified knots, clumps, and cavities shaped by asymmetric ejections. These features imply that dying stars often lose mass in episodic, uneven bursts, influenced by magnetic fields or companion stars. What once looked like smooth transitions now appear chaotic and sculpted by intricate forces. Some observations also suggest the presence of disks and jets around the central white dwarfs, remnants of material shaped by angular momentum and stellar rotation. These features had been speculated, but never confirmed with such clarity. In cases where a binary system is involved, the gravitational interaction can further shape the ejected material into spirals or arcs, now visible thanks to Webb's resolution. In larger star-forming nebulae like NGC 3324, Webb's ability to see through thick dust revealed hidden pillars, shock fronts, and narrow ridges of active collapse. These structures were previously masked by dust in optical images, leading to underestimates of ongoing star formation. Webb has shown that even quiet regions may be in the midst of forming stars. The detection of faint infrared emission also helped identify photodissociation regions, zones where UV light from nearby stars alters the chemistry of surrounding gas. These are transition regions between ionized gas and molecular gas and often contain the seeds of future star formation. Until now, their structures were theoretical or inferred only indirectly. In multiple nebulae, Webb has picked up fine rings and shells expanding outward from central stars. These are likely the results of thermal pulses or stellar convulsions and represent time-stamped records of how stars shed their envelopes. With each layer corresponding to a different eruption, these nested structures allow astronomers to build temporal maps of stellar decline. Webb's ability to capture faint hydrogen lines and molecular emissions also allow scientists to measure densities and temperatures in these previously obscured regions. This turns empty space into a dynamic, measurable environment, where interactions and flows can be modeled and compared with simulations of stellar death and gas evolution. The data also offer clues to how dust grains evolve over time. In cooler regions once thought to be featureless, Webb detected varying grain sizes and compositions, indicating active chemical processing. These grains may serve as raw materials for future planets, making these overlooked zones crucial to understanding cosmic recycling. Overall, what looked empty now reveals a quiet complexity, an interplay of light, chemistry, and memory preserved in dust. Webb doesn't just fill in blanks, it rewrites what we thought was silence, showing instead a chorus of subtle cosmic processes. Star formation inside forgotten dwarf galaxies on the cosmic edge. Dwarf galaxies, often overlooked due to their faintness and distance, are among the most ancient and fundamental building blocks of the universe. These small systems, some with only a few billion stars, have played a central role in cosmic evolution. With the James Webb Space Telescope, astronomers can now peer into their dim cores and outskirts, uncovering active star formation where we once saw only quiet dust and aging stars. One of the breakthroughs came from Webb's survey of the Sagittarius Dwarf Irregular Galaxy and other isolated systems on the periphery of the local group. Observing in the near and mid-infrared, Webb detected young, massive stars forming in pockets of dense gas, regions previously unresolved in older surveys. These discoveries suggest that starbirth in dwarf galaxies is not just a relic of the past. Some of these galaxies show clusters of bright infrared sources, interpreted as protostellar nurseries. Despite their low metallicity, meaning fewer heavy elements compared to larger galaxies, these dwarfs appear capable of sustaining star formation. Webb's instruments revealed that the processes of gravitational collapse and fragmentation occur even in these sparse, low-pressure environments. In galaxies like WLM or Wolf-Lundmark-Melotte, Webb uncovered filaments of cold dust spanning hundreds of light-years, with embedded stars at various stages of development. These filaments serve as scaffolding for star clusters, highlighting how even weak gravitational fields can organize matter on galactic scales. Spectral data show that these environments host molecules like carbon monoxide and ammonia, albeit in lower quantities than seen in the Milky Way. This suggests that while chemistry is more primitive, it is still active. These chemical traces help track gas cooling, turbulence, and feedback from young stars, crucial ingredients for continued star formation. Interestingly, Webb found that some dwarf galaxies show evidence of synchronized starburst activity. Rather than isolated random formation, stars in these systems seem to ignite in waves, possibly triggered by interactions with intergalactic gas flows or past galactic encounters. This pattern had been hypothesized but lacked observational proof until now. One unexpected result was the identification of extremely faint red stars in these galaxies, likely low-mass stars forming in environments with minimal shielding from radiation. These stars challenge current models, which predicted such objects to be rare in metal-poor galaxies. Webb's data indicate that the stellar population in dwarfs may be far more diverse than previously thought. Some dwarf galaxies also host globular clusters or remnants of ancient mergers. Webb's deep imaging reveals the layering of star formation epochs, with old stars mingling alongside newborn clusters. This blend paints a more continuous evolutionary picture than the sharp divisions once assumed between early and recent star formation. Because dwarf galaxies are less chemically evolved, they serve as analogs for conditions in the early universe. Observing active star formation here offers a glimpse into the processes that dominated during the first billion years after the Big Bang. Webb effectively lets us study near-field examples of far-field cosmological conditions. These galaxies also help refine feedback models. Webb observed the effects of stellar winds, radiation pressure, and supernova remnants in shaping surrounding gas, insights that inform how stars regulate further star formation in low-mass systems. The data are crucial for simulations that try to model early galaxy formation and evolution. Some dwarf systems contain extended gas halos, once thought inert, now showing faint infrared emission. These halos may represent future star-forming regions or residual gas from earlier activity. Webb's sensitivity helps map their structure and connection to the galactic core. What emerges is a universe where even its most modest members remain cosmically active. These dwarf galaxies, long assumed to be relics, are alive with starbirth, silent engines of light on the edge of the cosmos. Silicate-rich dust detected on extreme, glowing exoplanets. Some of the most surprising findings from the James Webb Space Telescope have emerged not from ancient galaxies, but from searingly hot exoplanets, worlds so close to their stars that their atmospheres glow like molten glass. In several of these cases, Webb has detected signs of silicate-based clouds, revealing that even in extreme conditions, minerals like quartz and olivine can exist as atmospheric dust. These observations challenge preconceptions about planetary chemistry under extreme heat. One standout observation came from the planet WASP-17b, a gas giant located about 1,300 light-years away. Using transmission spectroscopy, Webb detected spectral features corresponding to silicate particles suspended in its upper atmosphere. These signals appeared during the planet's transit across its star, when starlight filters through the atmospheric limb and picks up chemical signatures. The presence of silicates in a vapor or cloud phase suggests that temperatures in the upper atmosphere hover near the condensation point for these minerals. On planets like this, the atmosphere behaves more like a high-temperature chemical reactor, with continuous cycles of vaporization, condensation, and re-evaporation happening at supersonic wind speeds. These silicate clouds likely form on the planet's cooler night side, where vapor condenses into tiny mineral grains. High-altitude winds then redistribute these particles to the day side, where they are vaporized again. Webb's observations indicate these clouds are patchy and dynamic, driven by extreme temperature gradients across the planet. In addition to silicates, Webb has detected metal oxides and exotic compounds in some of these atmospheres, including hints of vanadium oxide and titanium hydride, molecules that form only under extreme temperatures. These findings expand the known palette of atmospheric chemistry, suggesting a broader diversity of weather than previously imagined. Some exoplanets show phase curves, brightness changes as they orbit, that reveal the heat distribution across their surfaces. Webb has used this technique to infer the presence of cloud decks composed of mineral dust, which redistribute thermal energy and affect how heat is retained or emitted. These insights help refine models of atmospheric circulation in tidally locked planets. The implications extend beyond chemistry. Silicate clouds affect a planet's albedo and emission spectra, changing how much light it reflects and emits. This in turn influences temperature profiles, photochemistry, and even the planet's long-term atmospheric evolution. In one case, the hot Jupiter HD 209458b exhibited signs of high-altitude haze that included crystalline silicates. These fine grains may contribute to scattering and light absorption, shaping the spectrum in subtle but detectable ways. Webb's resolution allows these components to be separated from other atmospheric gases. Such observations also challenge earlier assumptions that mineral clouds couldn't survive long in hot environments. Instead, Webb is showing that silicate-based weather is not only possible, it may be common among the universe's many superheated exoplanets. This invites a reevaluation of what we expect from planetary atmospheres under intense irradiation. Scientists are now comparing Webb's exoplanetary spectra with laboratory measurements of minerals to better constrain particle size, composition, and vertical distribution. These comparisons are essential for interpreting the fine structure in Webb's data and distinguishing between similar materials like enstatite and forsterite. The study of silicate clouds is also relevant for understanding planetary formation and migration. The materials detected suggest that elements like magnesium and silicon are present in the upper layers, hinting at the internal composition and geochemical history of the planet. Ultimately, Webb's infrared sensitivity turns these glowing, hostile worlds into windows for mineralogical study. What was once considered too hot for complex clouds is now a laboratory for silicate weather systems, dust storms, and cloud decks made not of water, but of rock. How Webb is confirming or challenging theories of dark matter. The existence of dark matter has long been inferred through its gravitational effects. It shapes galaxy rotation curves, bends light from distant objects, and forms the scaffolding for large-scale cosmic structures. But direct observation remains elusive. With its unprecedented infrared vision and sensitivity, the James Webb Space Telescope is now offering indirect tests of dark matter by observing gravitational lensing, galaxy formation, and the behavior of light in the early universe with new precision. One of Webb's key contributions lies in mapping massive galaxy clusters, where dark matter acts like a gravitational magnifying glass. Clusters like SMACS 0723 and Pandora show warped backgrounds where light from more distant galaxies is bent and distorted into arcs and rings. Webb can measure these distortions more accurately than ever before, providing a more refined estimate of the dark matter distribution within each cluster. These lensing maps help constrain how dark matter clumps together at small scales. Some theories predict that dark matter should form smooth halos, though others suggest a more granular structure made of compact subhalos. Webb's high-resolution images allow astronomers to detect subtle anomalies in lensing patterns that may distinguish between competing models. In some lensing cases, the light from background galaxies appears multiple times, forming nearly identical images due to gravitational bending. The slight differences in timing and brightness between these images allow scientists to test the distribution and behavior of mass, both visible and invisible, along the line of sight. Webb provides the clarity and infrared range needed to capture these subtle effects. Another avenue is the study of galaxy formation in the early universe. Dark matter is thought to have played a key role in structuring the cosmos, providing the gravitational wells where gas could collect and form stars. Webb has found unexpectedly massive and mature galaxies at very high redshifts, too early in cosmic time for standard models to fully explain. These findings force a re-evaluation of how dark matter halos grow and attract baryonic matter. Webb's ability to detect faint, distant galaxies also tests theories about dark matter's influence on reionization. If dark matter clumps efficiently, it should help create dense regions where the first stars and galaxies formed. The number and distribution of early galaxies observed by Webb thus inform how dark matter shaped the end of the cosmic dark ages. Some models of dark matter predict slight suppression of small galaxies in the early universe due to particle properties like warm dark matter, which would prevent small-scale clustering. By measuring the faintest galaxies Webb can detect, astronomers can look for the presence or absence of such suppression and use it to infer the nature of dark matter. In parallel, Webb is helping rule out or support alternative theories of gravity, such as modified Newtonian dynamics, or MOND, which try to explain galactic behavior without invoking dark matter. Webb's precise measurements of galaxy mass, star formation, and lensing contribute empirical data that these alternative theories must now confront. While Webb cannot detect dark matter directly, it offers the best view yet of the structures shaped by its gravitational influence. It reveals how light travels through space warped by invisible mass and how galaxies form in the gravitational wells dark matter creates. Future observations may refine these constraints even further. By repeatedly imaging lensing systems over time, scientists hope to capture micro-lensing events, brief changes in brightness caused by compact dark matter objects like primordial black holes or dark clumps. These would provide unique fingerprints of dark matter's physical form. For now, Webb is acting as both a cosmic mapmaker and a theory tester. It illuminates where dark matter must be based on the shapes and arrangements of galaxies, and slowly closes the gap between mathematical models and what the universe actually looks like. What Webb can't see: technical limits and the secrets still out of reach. Despite its groundbreaking capabilities, the James Webb Space Telescope has clear limitations. First among these is its observational range. Webb focuses exclusively on the infrared spectrum, meaning phenomena emitting primarily in ultraviolet or X-rays remain invisible. Thus, high-energy processes, such as black hole accretion disks or extremely hot stellar remnants, require other observatories to complement Webb's data. Webb's position at the L2 point, 1.5 million kilometers from Earth, offers unparalleled stability and thermal isolation, but prevents direct servicing. Unlike Hubble, which astronauts could repair, Webb's lifespan and operational adjustments are limited by its initial hardware setup. Instrument failures, fuel exhaustion, or unexpected malfunctions would significantly constrain future observations. Another limitation arises from Webb's sensitivity to bright infrared sources. Objects too luminous in infrared, like very close, warm exoplanets or stars with dense circumstellar dust, may saturate Webb's detectors. This saturation limits detailed study, forcing astronomers to use other telescopes or indirect methods to investigate these brighter phenomena. Webb also struggles with time-sensitive, rapidly changing cosmic events. Although capable of deep, detailed observations, the telescope requires carefully planned pointing and integration times. Transient phenomena such as short-lived gamma-ray bursts, sudden stellar flares, or fast-moving solar system objects pose observational challenges that Webb is not optimally designed to tackle. Resolving power, the telescope's angular resolution, is another constraint. While Webb significantly surpasses previous infrared telescopes, certain very distant or tightly packed structures, like binary star systems extremely far away or intricate star clusters in remote galaxies, may still appear blended or indistinct. Webb's resolving power, though extraordinary, has practical limits in spatial differentiation. Dust interference remains another issue. Although Webb peers effectively through many dusty environments due to its infrared capability, extremely dense regions of molecular clouds can still obscure underlying structures. Infrared light can penetrate deeper than visible light, but even Webb faces a threshold beyond which detail becomes inaccessible. Webb's instruments also have operational temperature constraints. The telescope's mirror and instruments must stay extremely cold, below 50 Kelvin, to minimize self-emitted infrared noise. This requirement limits the telescope's viewing angles, forcing it always to orient its massive sunshield toward the sun and restricting observational windows for certain celestial targets. The telescope is also sensitive to interference from scattered sunlight or thermal radiation reflected by its own components. Any slight misalignment of Webb's sunshield or unexpected thermal instability can introduce background noise, reducing observational precision. Such issues, while rare, require meticulous management throughout its operation. In terms of chemical detection, Webb's spectral resolution is exceptional but not infinite. Extremely subtle molecular signatures or rare isotopic ratios, important for precise chemical modeling, can remain elusive if their spectral features overlap or if signal strength approaches instrument noise levels. These cases require complementary observations from ground-based telescopes or future missions. Webb's infrared range also inherently limits its ability to probe the earliest moments immediately after the Big Bang. Light emitted during the cosmic microwave background era falls into microwave frequencies, requiring specialized observatories like Planck or future radio telescopes. Thus, Webb can look deeply into cosmic history, but not to its very origin. Data volume and transmission pose another practical limit. Webb generates vast quantities of data during deep field observations, yet the speed of communication from L2 to Earth is finite. This constraint requires careful selection of targets and prioritization of data transmission, occasionally delaying observations or limiting their frequency. While Webb pushes the boundaries of astronomy further than ever before, these inherent limitations mean some secrets of the universe remain beyond its reach, leaving room for future telescopes and missions to continue humanity's quest for cosmic knowledge. Why Webb's observations might rewrite the current model of cosmic expansion. The expansion rate of the universe, known as the Hubble constant, remains one of cosmology's most debated topics. Measurements from the cosmic microwave background, (CMB), and local galaxy observations currently disagree. Webb's high-precision infrared observations of distant galaxies and gravitational lensing systems could provide new insights that clarify or deepen this tension. Webb's deep-field observations have identified mature galaxies forming earlier in cosmic history than standard cosmological models predict. Such unexpectedly rapid early galaxy formation suggests that conditions shortly after the Big Bang may have been different. Perhaps expansion occurred at different rates or under conditions not yet accounted for by current models. One direct way Webb helps tackle the expansion question is through refined measurements of gravitational lensing. Massive galaxy clusters bend the light from distant galaxies, forming multiple images whose subtle brightness and positional differences depend on cosmic geometry. Webb's precision in mapping these distortions enables accurate, independent measurements of the universe's expansion rate. If Webb's lensing measurements consistently differ from predictions based on the CMB, this discrepancy could indicate a gap in our understanding of early universe physics. Possible explanations include the behavior of dark matter and dark energy, or modifications to Einstein's theory of gravity at cosmological scales, topics already actively debated in theoretical physics. Additionally, Webb observes Type Ia supernovae, key standard candles, used to measure cosmic distances. By studying these supernovae at greater redshifts and with higher accuracy than previous telescopes, Webb may reveal systematic errors in past measurements or uncover new variations in their luminosities. Such findings could adjust distance scales and alter calculations of expansion rates. Observations of variable stars like Cepheids, another critical rung on the cosmic distance ladder, also benefit from Webb's infrared clarity. Dust obscuration has historically complicated measurements of Cepheid brightness. Webb, capable of penetrating this dust, provides cleaner, more precise luminosity measurements that could revise the cosmic distance scale and thus influence expansion calculations. Webb's ability to detect faint early galaxies further impacts models of dark energy, the mysterious force accelerating cosmic expansion. Early massive galaxies imply faster early galaxy growth, possibly affecting how we model dark energy's impact over cosmic history. Any shifts in understanding dark energy directly influence predictions about the universe's future expansion. Some recent Webb observations suggest anomalies in galaxy clustering at large scales, potentially indicating variations in dark matter distribution or dark energy behavior. Such anomalies, if confirmed through larger surveys, could challenge the assumptions underlying the current lambda cold dark matter (LCDM) model, the standard cosmological framework. Webb's spectroscopic data also help measure cosmic chemical enrichment more precisely. Unexpectedly high metallicity in early galaxies could point to rapid star formation, implying different conditions for baryonic matter evolution. These observations challenge fundamental assumptions about how galaxies form and evolve, indirectly impacting models of universal expansion and matter distribution. Combining Webb's data with observations from other telescopes, such as ground-based optical surveys or upcoming missions like the Euclid satellite, will further refine our cosmological models. Discrepancies across multiple independent measurements could indicate fundamental new physics, forcing cosmologists to reconsider long-standing theoretical frameworks. If the current tension in expansion rates remains unresolved even with Webb's precise observations, cosmologists may have to entertain radical revisions of cosmic history. Alternative theories such as early dark energy, modified gravity, or non-standard particle physics might gain traction as scientists search for explanations consistent with all available evidence. In short, Webb's observational precision, depth, and breadth could compel cosmologists not just to fine-tune, but to fundamentally rewrite the current understanding of cosmic expansion. Each new measurement brings us closer to understanding whether our universe expands according to known physics or if entirely new concepts await discovery.